The most common type of 2D motion that we will encounter is motion in the vertical plane under only the influence of gravity. So this is similar to free fall motion, but now includes objects moving in 2D. So this could be something launched horizontally into the air, or launched from the ground at an angle, or maybe at a height at an angle into the air, so that now it's moving in 2D, but it's still acted on by only the force of gravity. So there's no air resistance, no friction, and no external applied forces. In this case, the object experiences an acceleration due to gravity, which is negative 9.8 meters per second squared, in the y direction only. It has zero acceleration in the x direction. This means that whatever x velocity it's initially given, it's launched with, that x velocity is constant for the entire motion. The y motion, however, will evolve similar to an object in free fall. Actually, if we had two objects and one was launched horizontally and one was dropped from the same height, they would reach the ground at the same time because the time only depends on the vertical motion. So in this case, we can use the four kinematics equations that we've seen before applied to 2 dimensions. But we need to recognize that the object is a projectile, so look out for things launched into the air, thrown, tossed at an angle, any kind of balls kicked into the air. Those are projectiles. And then remember these two accelerations. So remember that the vertical acceleration, AY, the y component, is negative 9.8 meters per second squared, and that the x component is 0. So let's look at some more properties of this motion by considering an example. Example 15, sketch the trajectory and velocity vectors of a kicked soccer ball. I'm going to use a color coding here, so the x components are in blue, the y components in red, and then the velocity vector, the full vector, will be in black. So one thing we know is that this is a projectile, so it's only experiencing an acceleration in the y direction. Once it's released into the air, even if it's kicked like this at an angle, only gravity is acting on it, which means it only experiences that negative 9.8 meters per second squared acceleration in the y direction. Ax is 0, so if it's kicked initially with a certain x component of the velocity, which I'll draw in here, that's Vx, that will remain exactly the same the entire time. So I can draw this Vx vector everywhere. I tried to draw it the same length and always horizontal because that is constant. So we know that Vx is constant for the motion. So this is the ball that was kicked here, and it makes this parabolic shape before it hits the ground. Now Vy will actually evolve in the same way as a falling object. So let's say it's kicked with an initial y velocity here. That's going to slowly decrease because of the acceleration until it reaches 0. At the maximum height, now we have Vy equals 0. Vx is non-zero. It's equal to the initial x component of the velocity, but we do have Vy as 0 at the top, which is analogous to what we saw in free fall. Now that negative 9.8 meters per second squared will start to accelerate the ball downwards. So now that starts to increase again, and this last one is just before it hits the ground or it's intercepted. Okay, so our net velocity vector will be the vector sum of these two quantities, which will look something like this. Look at the top, it's just Vx, so it's right along the same as our x component, both horizontal there. That's kind of hard to see. These are two horizontal line arrows there. And here, there. And I'll insert a better photo of this here. So there's a couple more things we can note about parabolic projectile motion of this type. So this is where something is launched into the air and it returns to the same height so that we have delta y is 0. So one thing we already mentioned is that the y component of the velocity is 0 at the maximum height. That's true anytime we saw for free fall Also, for any projectile, no matter what delta y is, at its very maximum height, the y component will be 0. Now, if it's symmetric like this when delta y is 0, what we know and what can be proved by the kinematics equations is again that we have Vy equal to negative V naught y. So when it reaches the same height, mine's just a sketch, but when it returns to the same height, the y component will be equal in magnitude to its initial y velocity, but now negative. So similar to what we saw in free fall, but again only for the y motion. Then also we know that because this is symmetric, it's going all the way up and coming down to the same height. We have the time that it takes to go up equals to the time that it takes to go down. So these factors are helpful sometimes when we're solving problems. We can use them to simplify. As I was saying, the 4 kinematics equations apply here for projectile motion, and this is what they look like for a 2D projectile. Let's go on to solve projectile motion problems using the process that we use for 2D kinematics. Okay, so we'll do the first example now, and I'll show you a general method for solving projectile motion problems with the first example. Example 16, a punter kicks a football at an angle of 30 degrees above the horizontal with an initial speed of 20 meters per second. A, what is the maximum height reached by the ball? B, how long has the football been in the air when the receiver intercepts it? And C, where should a receiver position himself to intercept it just as it strikes the ground? So I suggest always starting with a diagram for projectile motion. I find that really helpful. So we have something, football, that's kicked here, and then it's launched and it reaches the ground later, or the same height when it's intercepted here by the receiver. So we have an initial velocity of 20 meters per second at 30 degrees to the horizontal. Now I suggest making a chart just like this with our x information on one side and the y information on the other. And the very first thing you can always write in your chart for any projectile problem is the acceleration. So AY is negative 9.8 meters per second squared, and we know AX is going to be 0 since there's no horizontal acceleration. Then you can fill in the specific variables for your question. So one other thing we know is that delta y total is going to be 0. And we have the velocity, so we can find its components. So next step, once you've written in the given information, we want to add in the vector components. So this is at an elevation angle, which is an angle above the horizontal of 30 degrees. So it makes a little triangle here with V naught x and V naught y. So you can find the components as you have been doing so far. So V naught x is adjacent, it will be cos. We'll have 20 meters per second cos 30, which is 17.32 meters per second. And V naught y, which is opposite to the angle, will be sine. 20 meters per second sine 30, so 10 meters per second. All right, and we can plug them in. Vx is 17.32 meters per second, and V naught y is 10 meters per second. Remember, you can put V naught x here, you can put Vx, it's up to you because it's a constant speed, so they're both equal. But this is our initial y component of the velocity. All right, and the first question for A is what is the maximum height up here? So this is our delta y max reached by the ball. And we know that at that point, Vy final equals 0. So we want delta y max, and we have Vy final equals 0. So what I'm not going to use is delta y is 0. That's for the overall motion, where we're just looking at half the motion in this case, and we want delta y. So I'm going to choose an equation that has V initial, acceleration, V final, and delta y. So that's the one without time. Vy squared equals V naught y squared plus 2ay delta y, I'll label that as delta y max. And then we can solve here. So Vy final is 0. We get delta y max equals negative V naught y squared over 2ay. Okay, so that's negative 10 meters per second squared over 2 times negative 9.8 meters per second squared, which equals 5.10 meters. All right, now for part B, we're looking for the total time that the football is in the air. So we do have delta y is 0 now, moved it up, but we have delta y is 0. We'll look at the y information. The vertical velocity is actually what always sets the time. So 10 meters per second, acceleration is negative 9.8 meters per second squared, and we want time. So we'll choose choose an equation that has all of these variables that can find time. That's delta y equals v naught yt plus 1/2 a t squared. And notice how, just like we did in 2D kinematics, since this is 2D kinematics, I'm treating always the x and the y information separately. So looking here, if I wanted the time, I don't have enough information here to find it using my x coordinate information. I would need displacement, and we're going to find that, but we don't have it yet. So if we look in the y information, we do have enough information here to find time. Always check, because sometimes you'll need x information to find time, but in this case we can find it with the vertical information. Okay, so then delta y is 0. So we have 0 equals v naught yt plus 1/2 ay t squared. I'm going to divide this by t, which will cancel one factor of t from both terms, and 0. And then, so I get one factor of t here, we get t equals negative 2 v naught y over ay. So negative 2 times 10 meters per second over negative 9.8 meters per second squared, which gives me 2.04 seconds. All right, now for part C, we want to know where should the receiver position himself to capture the ball. So here, which is really asking us for this distance, delta x. So if we look in our chart, we want to find delta x, and we do know the time now, which is 2.04 seconds, since the time is the same, of course, for both of the coordinate information. For the x information, we have a constant velocity since a is 0. If you want, we're always going to use, you can think of it like this, we're always going to use this equation here in the x information for projectile motion, and ax is 0. So it's just this part of the equation that remains, which you'll notice is just the equation for displacement when we have a constant velocity. So this was way back to 2.1, I believe. So we get delta x equals v naught t, which is v naught x, by the way, or vx, so 17.32 meters per second times 2.04 seconds, which gives me 35.3 meters. When a projectile is launched from a height and returns to that same height, a formula can be derived to determine the range of the projectile. So the range means the horizontal displacement of the projectile, delta x, which you may also see called capital R for range. So let's consider this case just like the previous question, where delta y is 0. So making our chart, we have ax equals 0. Ay I'm going to write as negative g, just because I'm deriving a algebraic relationship here. So negative g. And then I have delta y is 0. And now we would have velocity components as well. So v naught is going to be, v naught x is going to be v naught cos theta, and v naught y will be v naught sine theta. Okay, so let's look first. If we want to determine delta x, in order to do this, I'm going to need to find the time. And there wouldn't be enough information in this x direction with just v initial and a in order to find time, so we'll look at our y information and use this to find the time. So we choose an equation with ay, delta y, v naught y, and t, which is this one, delta y equals v naught t y plus 1/2 ay t squared. And now we know delta y is 0 like we did in the last problem. So we have 0 equals v naught yt plus 1/2 ay t squared. And then I'm going to divide the whole equation by t. So we have v naught y, 0 equals v naught y plus 1/2 ayt, which gives t equals -2 v naught y over ay. And now I'm going to plug in what we have. So v naught y is v naught sine theta, and ay is -g. So we're at t equals -2 v naught sine theta over -g. So this is 2 v naught sine theta over g. Okay, so we have that relationship for the time. Now we would go to our x information and use the equation for x displacement, like I showed you, v naught x t, in order to find the range. So when we plug this in, we have v naught x, which is v naught cos theta, times t, 2 v naught sine theta over g, which gives me 2 v naught squared sine theta cos theta over g. And I'm going to make use of a trigonometric identity here that says that 2 sine theta cos theta equals sine 2 theta. Don't worry if you haven't seen that before, you won't have to use that yourself, but I want to show you where this equation comes from. So plugging that in, this all together equals sine 2 theta. So we have v naught squared sine 2 theta over g. And this is called the range equation. Delta x equals v naught squared sine 2 theta over g. It's a really interesting equation because it tells us that as long as we know the initial speed and the launch angle of the projectile, we can jump right to finding how far it travels horizontally. Now remember that this equation only applies when delta y equals 0 overall. Another use of this equation is that if you wanted to find the launch angle to produce a certain range, we could do that if the initial speed is given. And something interesting is that because a property of any sine function is that it has two positive solutions, there's actually two launch angles that would produce the same range. So we could have a projectile launched at one angle, traveling maybe like this, and then at this angle, and then another launched at a lower angle, that would produce the same range. And you won't have to find both angles in this course, but it is something to think about. Example 17, use the range formula to calculate the range in the previous example. In the previous example, number 16, we had a projectile, a football, that was launched at 20 meters per second at 30 degrees. So now we can cut and skip to this part of calculating the range, which we did in 2 steps previously. So 20 meters per second squared sine of 60, because it's sine of 2 theta, right? So we do twice of 30, and then divided by 9.8 meters per second squared, and you could check, we again get 35.3 for the range. Example 18, a projectile is shot from the edge of a cliff 125 meters above ground level with an initial speed of 65 meters per second at an angle of 37 degrees to the horizontal. A, determine the time it takes to hit point P. B, determine the projectile's range. C, find the velocity components just before the projectile hits P. D, find the magnitude and the direction of this velocity vector. And E, find the maximum height reached above the cliff. Okay, so again, I think it helps to sketch the projectile. We have it launched off the cliff here, which is at a height of 125 meters, and then returning to the ground. Making our chart, and then AX equals 0, and AY is negative 9.8 meters per second squared. Now let's fill in the other information we have. Overall here, delta Y is negative 125 meters. It's going to move down a total displacement of the height of the cliff. And then we also have the components which we can find. So V naught X will be 65 meters per second cos 37 degrees. which is 51.9 meters per second. And then V naught y is 65 meters per second sine 37, which is 39.2 meters per second. And then we can put that into our table as well. So V naught x or Vx, they're both 51.9 meters per second. And then V naught y is 39.2. All right, and question A is asking for the time. How long does it take this projectile to hit the ground? So looking at our information, since we don't have the range yet, we can't use the x information to find time. So we'll use the y information to find time and choose an equation with these 4 variables, which is, yes, going to be the quadratic. So delta y equals v naught yt plus 1/2 ay t squared. All right, so I recognize that nothing is 0 in this equation. All the variables are non-zero, and we can plug in the numbers. Negative 125 meters equals 39.2 meters per second t plus 1/2 times negative 9.8 meters per second squared t squared. So this is negative 4.9. I'm going to move it over and it becomes positive 4.9 meters per second squared t squared. Moving this over as well, it's negative 39.2 meters per second t, and then we have minus 125 meters equals 0. So plugging it into the quadratic formula, we have t equals negative b, so 39.2 meters per second, plus or minus the root of negative 39.2 meters per second squared minus 4a c all over 2a. And if you plug that in with both a positive and a negative sign, you'll get negative 2.44 seconds and 10.4 seconds. So of course we know our positive solution makes sense here. So 10.4 seconds is the time that this projectile is in the air. All right, now for part B, we need the range of the projectile. We cannot use the range equation because delta y is not 0 overall. It doesn't return to the same height. But once we have the time, we really don't need it anyway. Delta x is v naught xt. So it's nice and easy to just find the range here, 51.9 meters per second times 10.4 seconds, which gives 540 meters for the horizontal displacement. Okay, I've had to make more space here. Part C asks for the final velocity here just before the projectile hits the ground. So it's probably at an angle, something like this actually. And we'll want the x and the y components here of the velocity, vx and vy. Now we know that vx is constant. There's no x acceleration, so that one's still going to be 51.9 meters per second. But we will have to calculate how the y velocity has evolved. So we have all of this information in the y direction, so you really can choose any equation with vy. I'll use the first one, vy equals v naught y plus ay times t. So we have 39.2 meters per second plus negative 9.8 meters per second squared times 10.4 seconds, which gives me negative 62.7 meters per second. So that's the y component just before it would hit the ground. Okay, in part D, we want to find the magnitude and direction of that velocity vector. So the magnitude v will be the root of 51.9 meters per second squared plus negative 62.7 meters per second squared, which is 81.4 meters per second. And then the angle theta here will be tan inverse of Vy over Vx. So tan inverse, or arctan, of 62.7, again using the absolute value in the tan function, over 51.9, which is very close, 50 degrees, 50.4 maybe, depending how you round it here. So that means our velocity vector will be 81.4 meters per second at 50 degrees below the horizontal. Note that this is 50 degrees towards the downwards direction, so we don't want to use north, south, east, and west in that case. Okay, and then the last part is what is the maximum height of the projectile above the cliff? So at its maximum height, remember that Vy equals 0. So we can use the equation without time, Vy squared equals V naught y squared plus 2a delta y. This is a vertical quantity, so of course we're using our vertical information and then solving for delta y. And that's the maximum height, it's not the overall displacement. Okay, so that's 0, and then delta y max is going to be negative V naught y squared over 2ay. So negative 39.2 meters per second squared over 2 times negative 9.8 meters per second squared, which gives me 78.4 meters for that maximum height above the cliff. Okay, so we've solved for just about everything you can solve for a projectile motion question like this, so have a look at that and let me know if you have any questions. Romeo is chucking pebbles gently up to Juliet's window. He wants the pebbles to hit the window with only a horizontal component of velocity. Romeo stands 4.5 meters below the window and 5 meters from the wall. How fast are the pebbles going when they hit? Alright, so let's draw a diagram. I've got that here. And then again, list our information in the chart. This one's asked a little bit differently. So we have delta y and delta x given. Delta y is 4.5 meters and delta x is 5 meters. And then we know that when they hit the window, there's only an x component. Vy will be 0 at that point. So Vy final is 0. And we're looking for Vx. How fast are they going when they hit? So looking at this, we need to find time in order to be able to find Vx with the x information. So we'll go to the y information to find time. And when we do that, we will need the initial y velocity first. So let's find that as our first step. We have Vy squared equals V naught y squared plus 2a delta y, since we don't have time yet. And then we know final y is 0, so V naught y squared equals negative 2a delta y, ay delta y. And then we can just solve here, so V naught y will be the root of negative 2 times negative 9.8 meters per second squared times 4.5 meters, which gives me 9.4 meters per second. Okay, now we can use that to find time because we have Vy equals V naught y plus AT. Vy is 0 again, the final y velocity. So I get t equals negative V naught y over A, which is negative 9.4 meters per second over negative 9.8 meters per second squared. So 0.96 seconds. And that's what we needed. Now the last step we can go to is finding Vx. This is the final velocity, which is how fast they go when they hit, which we were asked for. It's also the initial x component of the velocity since it's constant. So 5 meters over 0.96 seconds gives 5.2 meters per second, and that's our answer to how fast the pebbles are going when they hit. So again, just make sure to draw your diagram, write your information, and then we can kind of piece together what we need to find in order to get to the final answer by choosing the appropriate equations as we've done before. Example 20, during a serve, a tennis player aims to hit the ball horizontally. A, what minimum speed is required for the ball to clear the 0.9 meter high net 15 meters from the server if the ball is launched from 2.5 meters high? B, where will it land on the other side? All right, I've drawn kind of a rough diagram here, but the ball is hit here horizontally, so we know V initial y is 0. And then it's going to clear this. This is the tennis net here that's 0.9 meters high. So since we know its displacement at that point, let's consider this point where it just clears the net. And then filling in the chart, AX and AY we always have. We know that this net is 15 meters from where it was hit. So it's traveled a horizontal distance of 15 meters. We have acceleration, we have V initial y is 0 since it was hit horizontally. And now we have delta y as well. So delta y is y final minus y initial, which is 0.9 meters minus 2.5 meters. So negative 1.6 meters. You can also just see that kind of that it's moved down 1.6 meters from where it started. All right, so we're going to need to find time because eventually we want to just find out how fast it was going. Vx is our unknown. How fast is it going to clear the net? And we will, as usual, need time to do that. So I'm going to use the formula delta y equals v naught t plus 1/2 at squared based on the information that's given, and time is the unknown. And then v naught 0. So we end up with t equals 2 delta y over a and the root of that. Okay, so I'll need more space down here. So that means that our time, and this is for part A, is going to be the root of 2 times negative 1.6 meters over negative 9.8 meters per second squared, which gives me 0.571 seconds for the time. All right, now with that time, we can figure out the x horizontal velocity that it was hit with. So we have Vx equals delta x over t, just the constant velocity formula. So that's going to be 15 meters over 0.571 seconds, which is 26.3 meters per second. Okay, now in part B, we're asked how far it lands on the other side of the net. That's our unknown here. So let's find the total displacement from when it was hit, assuming that it's traveling at this speed so that it just clears the net, and then we can subtract the 15 meters to figure out how far it went behind the net. Okay, so it's going to look very similar to what we did for part A. The difference is this displacement. Now it travels all the way, let's go back, from the top to the ground. So from where it was hit to the ground. So we now have a delta y of negative 2.5. Negative 2.5 meters. Everything else is the same, so we have the same formula here, but it will be t equals the root of 2 times negative 2.5 meters over negative 9.8 meters per second squared, which gives me a new time of 0.714. So this is the time that it takes to hit the ground, and before we found the time it took just to reach the net. And then our total displacement will be Vx times t. So the speed we found, 26.3 meters per second times 0.714 seconds, which is 18.8 meters. Okay, so it reaches the distance of 18.8 meters from where it started, which is 18.8 minus 15 equals 3.8 meters behind the net. That's where it lands. Okay, so its final displacement where it hits the ground after just clearing the net is 3.8 meters behind it. Okay, that's all for this section. Let me know if you have any questions on any of this.